This is an absolute value inequality. And from what we know about absolute value, this is a graph of the solution set. All of the numbers less than or equal to negative 42 have absolute values which are greater than or equal to 42. And of course, all of the numbers greater than or equal to 42 also have absolute values that are greater than or equal to 42. If we modify the inequality so that it's just the absolute value of a number is greater than 42, the graph changes just a bit as the negative 42 and the positive 42 are no longer included in our solution set. Now here's another inequality. The absolute value of a number is less than or equal to 42, and here is the graph. It's all of the numbers from negative 42 through positive 42. And if we change it slightly, as shown, to the absolute value of a number is less than 42, the graph changes so that the negative 42 and the 42 are the boundaries of our solution set, but they are not included. Now we're looking for numbers that have an absolute value which is greater than or equal to negative 42. Well, all absolute values are greater than or equal to 0. Therefore, all numbers have an absolute value greater than or equal to negative 42. So rather than graph this solution set, we'll just put the capital letter R, which states that all real numbers work in this inequality. And if we change it as shown to just the absolute value of a number is greater than negative 42, it's still true for all real numbers. But now you can probably guess where we're going. The absolute value of a number is less than or equal to negative 42. Well, no absolute values are negative, and therefore none can be less than negative 42. So there are no solutions to this inequality, and the same for the one at the bottom. There are no numbers that have an absolute value less than negative 42. So the fourth inequality also has an empty set for its solution set. Here's one a little more complicated. Well, we're going to split it into two parts, just like we did for equations in the previous lesson. But you'll notice in most textbooks, when you split it in two parts and change the right side to the opposite of what it was, changing from 4 to negative 4, you also reverse the sense of the inequality as shown. That may be understandable if you go back and look at the first slide for the absolute value greater than or equal to 42. Anyway, we solved these two inequalities. And on the first one, we added 8 and divided by 2. And on the second one, we add 8 and divide by 2. And then we looking for a number that's greater than or equal to 6, as well as numbers less than or equal to 2. And it's an OR problem because there are no numbers that are both greater than 6 or less than 2. So the arrows go in opposite directions as shown. And to check your work for this inequality, pick a number from each of the three regions separated by the 2 and the 6. Pick a number greater than 6, such as 7. Plug it in for n in the original inequality and see if it's true, and it will be. Then pick a number between 2 and 6, such as 3, and plug that in and see if that makes the inequality true. And it won't be true. That's why we didn't shade that area. Then pick a number that's less than 2. 0 works fine. And if n is 0, see if the inequality is true, and it is, and that's why the graph is shown. Now we have a similar equation, only this equation, the inequality is less than or equal to, where the previous one was greater than or equal to. We split it as shown, making the 4 positive on the left, as it was in the original inequality, but changed to negative 4 on the right. We've also reversed the sense of the inequality on the right. We solved the 2 once again by adding 8 and dividing by 2. But now we get n is less than or equal to 6. N is greater than or equal to 2. That's an n problem. We're looking for the numbers 2 through 6. Can be written as what I call an inequality triple. 2 is less than or equal to a number which is less than or equal to 6. And there's the graph. Here's another inequality. We might be worried at the beginning because the right side is a negative, but we start right out by adding 56 to both sides. And now we have one that we can handle. We break it into 2. There's the left side. There's the right side. The 23 changed to negative 23, and the less than was reversed to greater than. And now we're going to add negative 8 to both sides on the left, divide by 5. We're going to add negative 8 on the right, and then we're going to divide by 5. And there's our two numbers. N is less than 3, and n has to be greater than negative 6.2. We can write it as shown, and here's the graph. There is one more method that is often used for solving absolute value inequalities. And while most textbooks that I've used have shown the method that was used in the previous examples, the method that I learned years ago, and the one I tend to use, is the method I'm about to demonstrate. On this particular inequality, of course, we would add negative 5 to both sides and get that the absolute value of 9n plus 12 is greater than 6. But now is where the method changes. We stop worrying temporarily about the inequality and we pretend that it's an equation. And so you'll see I've put equal signs in orange. So for now, we're just going to solve the two equations. 9n plus 12 is equal to 6. 9n plus 12 is equal to negative 6. We're going to add negative 12 to both sides and get in the left 9n equals negative 6. Divide by 9 and we get n is equal to negative 2/3. We add negative 12 on the right. We divide by 9 and we get n is equal to negative 2. Then we start with our number line and we mark the negative 2 and the negative 2/3 in their proper order. And now to determine how to shade it, we're going to test a number from each of the three regions marked off by the negative 2 and the negative 2/3. We're starting on the far right, and we're going to try a number that's easy to work with. How about 0? We go way back to the original inequality and we plug in 0. Or if you like, we substitute 0 in for the letter n. Well, 9 times 0 is 0. 0 plus 12 is 12. The absolute value of 12 is still 12. 12 plus 5 is 17, and now we have a true or false. Is 17 greater than 11? Yes, it is. So the 0 worked, and we shade in that entire section, all of the numbers greater than negative 2/3. Now we try a number in between. Negative 1 works, and we substitute that in. And 9 times negative 1 is negative 9. Negative 9 plus 12 is positive 3. The absolute value is still 3. 3 plus 5 is 8. We have another true or false. Is 8 greater than 11? It is not. So we don't shade this area in. And we go to the area on the far left, and we're going to try negative 3 because it's less than negative 2. And we substitute that in, and we get 9 times negative 3 is negative 27. We add 12, we get negative 15. We take the absolute value, we get 15. We add the 5, we get 20, and we ask ourselves, is 20 greater than 11? And it is. So we shade it in, and now we've got the graph. We can write it out as shown. N is greater than negative 2/3, or n is less than negative 2. It's another method that can be used when solving absolute value inequalities. Solving inequalities that involve absolute value is much the same as solving equations that involve absolute value. Some extra steps are required to determine how to graph the solutions. Two methods for doing this were outlined in this lesson.